Hey, welcome back. We are in section 6.5, which is on natural logarithms. Natural logarithms are actually logarithms that are extremely common, but we already called logarithms with a base 10 common logarithms. So what else are we to do but make up a new name? So we called them natural logarithms. And I suppose it's because they naturally occur in very many models. They naturally occur in a lot of systems that biological models, financial models, they're kind of everywhere. So natural logarithm is a logarithm with a base e. So we see the base e quite a bit. It's in a lot of mathematical applications. But if I have, let's say, e to the x equals y, I can rewrite this as a natural logarithm with a logarithm base e. So it's log base e of y is equal to x, right? And mathematicians, historically lazy, we hate to write the same thing over and over and over again. So instead of these four characters, log base e, we shorten this down to just ln. So instead of writing log base e, we just write ln for the log base e. So I would have ln y equals x. And this then is our natural logarithm, the logarithm naturel. I think it's a French guy that made us do this, but this is our natural logarithm. It's just the logarithm with a base of e. So we might see this as something like e to the third is equal to x, right? To rewrite this, I would simply then write that this is equivalent to the natural log of x is 3. Okay. We might also see something like, say, natural log of e to the 4. If we want to evaluate this, I would say this equals something. I don't know what it is, but let's call it x. And then if I rewrite this, the natural log is that base e. So that is to say that e to the x is equal to e to the 4 if I were to rewrite this as an exponential. And therefore I can tell that x has to be equal to 4 in order for that to work. If I have, let's say, the natural log, let's say e to the 10. Again, I want to call this x. If I'm to evaluate the natural log of e to the 10, I want to say this is equal to something. I don't know what that is. But to evaluate this, I again take the exponent, I take the e raised to the x, write it in exponential form, is equal to e to the 10. And then of course I can see that x has to be equal to 10 for this to make any sense. Right? And so between these two examples we can kind of note something. If I have the natural log of e to a power, it ends up being that power. Right? Natural log of e to the 10 ended up being 10. Natural log of e to the 4 ended up being 4. And that's one of the nice little properties that you'll notice. And it doesn't just work for natural logs. Anytime you have the base and then the same value raised to a power, it ends up being that power. But we're going to write this here as a natural log property. That is to say that if I have the natural log of e to any power, x, let's call it a, so it doesn't look like we're trying to solve something here. Natural log of e to any power, a for any, is equal to a. It always ends up being just that a. So I can skip going through the writing process to rewrite this as an exponential. If I have something like, say, the natural log of e to the 3.2, that's going to be 3.2. That's what it'll be. We saw in the last section a couple of logarithms that we evaluated. And in your calculator, you should also have a natural log button. It should be near your log button, or sometimes you have to hit second and then your log button to get to it. But it should be there. If you have a log button, you should have a natural log button on your calculator as well. And if I want to evaluate, let's say, the natural log of whatever, 2.5, right? I can think of this the same way we messed around with the common logs. I can say, well, this has to be equal to something. Let's call it x. And to rewrite it as an exponential gives me e to the x equals 2.5. Now this one's a little bit harder to imagine because it's hard to play with exponents of a number that's not 10. For this example, e, which is 2.7 something something something, would be larger. If x is 1, e to the 1 is larger than this number, so this number is going to be close to 1 but lower than it. So I should end up with something between 0 and 1 but closer to 1. And that's harder to play with because it's harder to take 2.7, some infinitely long string of numbers, and say, oh, if I multiply this by itself, what do I get? And multiply it again, what do I get? It's harder to do it than with the common logs or base 10 stuff. So this becomes a little bit less helpful. So we're just going to plug it straight into the calculator. Right? The calculator, just ln 2.5. What do I get? I get 0.916 something something. We'll just cut it off at 3 digits. 0.916 something something something. It goes on forever. Right? It's another irrational number. Good. How about, say, the natural log? One that you'll see a lot, the natural log of 2. If I plug that into my calculator, and you should do this as well just to make sure that you can. But natural log of 2 is 0.693, and that one goes on forever, yada yada yada. Right. You'll also take the natural log of 1/2 quite often. And it's interesting here, but if I take the natural log of 1/2, it's this same number, but negative. This is negative 0.693, blah, blah, blah. Right? And that's also kind of a nifty little property, but if I take the natural log of one number and the natural log of its reciprocal, the values will just be the opposite values of each other. With this, we would also then end up having to evaluate exponentials. So if I have something like, say, e to the 4th, and I need to evaluate e to the 4th, again, I should have a button that has an e, or sometimes it's an e with a little x raised, or sometimes it's exp. Depending on your calculator, you should have something that looks like this, right? If I want to evaluate this, though, I'll just take e, raise it to the 4th power, and if I do that, here I get 4, oh, just kidding, I have some stuff in there still. I get 54.598. And again, this number keeps going on and on and on, dot, 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 goes forever, right? If I want to evaluate something like, say, e to the negative 4, what do I get here? Here I get 0.0 183, and dot dot dot, that one goes on forever as well. Right? So know how to play with these, especially if you get something a little complicated up in the numerator, or even something like a negative might throw you off. In some calculators, the minus sign is distinct from the negative sign, so know which one to use or how to use that appropriately. Let's take a look here. Let's see what else. Yes, of course. All right. So let's graph. We want to take a couple of functions and graph them on the same set of axes. So we want to graph, let's say y equals the natural log of x, and let's say y equals e to the x on the same set of axes. Right? Now, the numbers are going to be pretty close to the bottom in this section in the book. If you just scroll down below this video in the actual book, you'll see the numbers pulled here. The kind of trick here is that if I have y equals the natural log of x, I can rewrite this as e to the y equals x, and then pick nice values for y and figure out what those x values are. So if I do that, I'm going to figure out a couple of values like -2, -1, 0, 1, and 2, plugging those into for y and then figure out the x values, right? So that is to say, if y is -2, I'm taking e to the -2, and e to the -2 is 0.135. Okay. And I suppose I can cheat and steal these numbers. Oh, they rounded them pretty small. Let me just do these. E to the -1 is 0.367 something. I would just round that to 0.37. E to the 0 is going to be 1. E to the 1 is my 2.718. And then e squared is, I don't know. Let's see. 7.38. Right? Now, since I'm graphing these, I really don't care about how accurate they are. In the book, they just say, we don't really care about all these digits. This is somewhere around 0.1. Because when I go to graph this, x is 0.1, y is -2, so -2 is here, let's say 1 is here. By the time I actually get my dot, that dot is so humongous compared to any level of accuracy I might get one more digit past that 1, that it doesn't matter. It doesn't make any difference. So I'll round this to say 0.4. I did this on the wrong side. Yoink, that should be there. If x is, let's say, 0.4, somewhere in this neighborhood, y is -1, so I get something like that. If x is 1, then y is 0. X is 2.7, so pretty close to 3 before y hits 1. And then I'm all the way to 7.3, so, way over here. Let's call this 8 before I hit 4. And we can see that logarithmic curve played out. Right? Now if I go and do the same thing for y equals e to the x, let me throw these values right here in black. This time I'm going to plug in values into the x and figure out my y values. I'll do the same values, -2, -1, 0, 1, and 2. But if x is -2, that gives me e to the -2. That's this 0.1 that we just got. If x is -1, I have e to the -1. You'll notice that that's that 0.37 yada yada number. If x is 0, that's e to the 0, which is just 1. If x is 1, that's e to the 1, that's the 2.7. And if x is 2, that's e to the 2, that's 7.3, yada yada, blah blah blah. And you'll notice here that these points, 0.1, negative 2, you just flip your x and y, you get negative 2.1. 0.37 and negative 1, flip those, you get that negative 1 and that negative, or that 0.37. 1, 0, flip it, you get 0, 1, 2.71, flip it, 1 and 2.7. So all we're doing is taking our x's and our y's and flipping them, and when that happens, that's called simply an inverse function. If your x's become your y's and your y's become your x, you simply have an inverse. And that's the point of this exercise here, graphing these on the same thing, is to see that they are indeed inverses of each other. So I'm going to erase this so we can see the graph here. But the graph will asymptotically come off of that x-axis and go up into an exponential. And on inverses, you can plant the line y equals x, and one should mirror the other one across that line, and these guys do. Let's graph another one of these. Let's graph y equals the natural log of x minus 4. So again, in order to play with this, I want to rewrite this because I don't know how to take the natural log of values very easily in my head, but I can do it on exponentials much easier. But at the same time, I'm going to end up using a calculator anyway, so you may just be able to throw in values of x and take the natural log of those. Let x equal, well, it can't be anything less than 4. Because if it is, you're subtracting 4 and you get a negative number and it won't work. So I could plug in, say, x is equal to, if I wanted to, maybe 4.1, 5, 6, 7, some of these values, right? But what's really going to happen here is that this thing is simply going to be shifted to the right by 4. So all I really need to know is that my natural log came asymptotically off of the negative y-axis, goes through this point 1, 0, and then goes off kind of as an exponential explosion in x. And having minus 4 in here is just going to take all of these numbers and shove them to the right by 4. So 2, 3, 4, 5 happens here at 5, 0. Just shifted this point 1, 0 to the left by 5. Everything else shifts to the right by 5. The asymptote here at x equals 0 gets shifted to the right by 4. I think I said the wrong thing. Everything gets shifted to the right by 4. So 1, 0 moves to the right by 4, 2, 5, 0. The asymptote that would normally be on your y-axis gets shifted to the right by 4. So I'm asymptotically leaving this line at x equals 4, still hitting this pivot point at 5, 0, and then exponential explosion in the x direction. And so that's all it is that that logarithmic graph that got shifted to the right by 4. All right. Thank you all, and I will see you guys next time.